Okay, this will be a demonstration of some natural language processing techniques using Python and SciKit Learn. This is actually going to be an example from a data challenge that was sent to me by a company that I was interviewing with. And so this is exactly the kind of thing that you might expect to run into if you're applying for jobs where natural language processing is on the list of required skills. In this case, the data set we'll be working with is this one here. We have these 5 columns of information: date, category, text. In this case, it's text of customer complaints, and then state and partial zip code. There are 50,000 plus examples here. The number of categories is 90, and they have names like deposits and withdrawals, loan servicing payments, incorrect information on credit report. It turns out that all the complaints have something to do with credit problems, credit situations, for the most part predatory lending type situations. So enrolled me in auto pay without my permission. Amount on credit report does not match what is owed. Nation Star Mortgage threatened me with enforcement of fraudulent document claims, full deniability. Anyway, the nature of the complaints is all sort of credit problems and predatory lending, and they're all sort of the length of an email. So we'll take from Python's SciKit Learn package. From feature extraction, we'd like count vectorizer and TF-IDF transform. This count vectorizer will take the text and parse it into a vector containing the number of occurrences of each term in the text, each word in the text. TF-IDF transform stands for term frequency times inverse document frequency transform. This is a common way to weight the counts vector that you've generated such that common terms get lower weight and rare terms get higher weight, because of course the rare terms are going to be those that tend to characterize the document. We're going to use a stochastic gradient descent classifier. You could use whatever classifier you want, but in this case I'm going to use this one. And then we'll take these 3 things and put them into a pipeline and use grid search CV to vary parameters, input parameters of those 3 pipeline pieces, and see if we can optimize the classifier. So we read in the data frame, we fill in missing values, we take the pieces of the data frame out into lists, we actually go ahead and append the state and zip code to the end of the text. So the state and zip code are actually going to appear in the text as just other terms, and these could be interesting characteristics of where complaints are originating from. At this point, we're going to restrict the categories that we consider to ones that have at least 3 complaints to train on. 3 is a rather ridiculously low number of training examples, but that's where we're going to start. So of the, so the pipeline we're going to define here is to use the vectorizer, then the TF-IDF transform, and then the classifier. And we will run our grid search over these variations of parameters. You could choose whatever parameters you want to vary. In this case, I'm choosing just a few of them so that it actually finishes in a relatively short amount of time. But max df for the vectorizer means, okay, do we want to consider 1.0, meaning all the terms, no matter how frequently they occur in the documents? 1.0 means they occur in every single document, 100% of the time. Or for 0.5, are we going to throw out, in this case, the top 50% most common terms in the set of documents we have? N-gram range, 1.1 implies that we're only going to consider single terms or unigrams, and 1.2 means we'll consider single terms and pairs of adjacent words, unigrams and bigrams. TF-IDF, true or false, this is just on or off. Do we want to use that weighting scheme that favors rare words? And then here the regularization parameter for the classifier. When we run this, it takes some time, so I'm not going to run it live, but I'll just show you the results. In the first case that we're going to consider here, we retain 87 out of the original 90 categories, 99.9% of the data. Again, we just threw out the ones that had less than 3 complaints associated with that category. So we search over these parameters. We found that with this parameter set, we're doing the best job possible. So regularization, TF-IDF on, throw out the 50% most common terms, and consider unigrams and bigrams. And we get a 57% accuracy of our classifier. We'd like to do better than that, but like I said, we're considering these cases, these categories in which we have very few training examples. So that's kind of, when you have just a handful of training examples, you don't really expect to get a great result, a meaningful result. So instead, if we up that number to categories which have at least 1,000 complaints associated with them, we find the following result. This is just changing that number from 3 to 1,000 and running again. Now we've retained 15 categories. We've thrown out most of the categories because only 15 of them have 1,000 or more complaints. However, they're still retaining 72% of the data. So we find that most of the complaints fall into those 15 categories, 72% of them. We get the same set of parameters that do the best job of fitting the classifier, so that's good. We haven't changed anything there. But our accuracy goes up to almost 70%. So what we find here is that essentially we can do already a decent job of categorizing these complaints just by considering ones where there are more training examples. So if we had more than 1,000 training examples for every category, we could expect to do 70% classification correct, 70% accuracy on the entire data set. So one way to go about this would be to try to generate a bigger data set and just have every category represented by at least 1,000 examples, training examples. Alternatively, you could try to reduce the number of categories. So these, if you read through the complaints, they're all very similar. And so it seems like it might make sense to approach this from a clustering perspective and look at where certain categories tend to cluster together so that you could maybe compress them into one category. And that would raise the total number of complaints in each category and reduce the total number of categories, and you could do a better job. Ultimately, you'd like to be able to automatically classify complaints as they come in and have it be 100% correct, but this is the kind of thing you can achieve by just running a simple pipeline with some of the packages in sklearn. So that's an example of some natural language processing techniques. There are a lot more to work with out there, and there's also sentiment analysis and other approaches to classifying text. But I'll leave that for another time.